All right, in this video, we are going to continue our discussion of the malware lab. So this is the final video of that series related to malware. So if you remember, the first video was the malware explanation, right? The explanation of the lab, how everything should be done. So it's kind of like the presentation. Then after that, we did the feature extraction, so how we go from log files to actual vector space representation of the data. Then after that, we did the machine learning part with the Weka program. Then after the Weka program, we did the machine learning part again with sklearn. In this video, we are going to continue. We're going to do the final part now. We're going to still do machine learning, but now we're going to do the machine learning with TensorFlow. So we're going to build a deep neural network and see the results. So since this is a video, I'm not going to really explain a lot of the theory of deep learning or anything like that. I've already done this in the lectures related to deep learning, so you can go back to the sequence of videos related to linear regression, logistic regression, neural networks, and deep neural networks. So in those videos, I've explained how the code works, and I've explained the theory behind deep neural networks and TensorFlow. So I recommend that you go back to those videos if you haven't seen them already before you do this lab. All right, so basically here you can see we have the files in our file system. We have this file, log file features.csv. This is the data. So this is the data file. We've already converted it to the vector space model, so it's ready to be analyzed. Notice we just have one data set. We're going to split it into train and test. And then we have here our code filelist_tf.py. Basically, this is the code that we provide, and I'm going to just explain how it works. All right. So here it is. As you can see, this is now whereas in the videos I kind of had screenshots of a lot of the code. Here you can see all the code from beginning to end. You can also download this code from the GitHub repository. It's loaded there. All right, so the basic idea with this, for your lab assignment, you will have to create several architectures. All right, so here I'm just going to provide the example of one architecture, but you should create several architectures based on the videos that you saw and compare the results, right? So you can, let's say, a neural network versus a 2-layer deep net versus a 4 or 5-layer deep net, and see how it performs. Our environment here is that we're just working on this, this data set is small, so we're doing this on a VM. The next lab that we're going to do, the network intrusion detection lab, is going to have 1 million records, so that one we're going to do in a GPU just to kind of, it'll be, like our big data kind of lab, and so we will address some of those issues there. But this one, there's no issues with the data size or loading the data. It's pretty straightforward. But this is, a good example of how to build a deep neural network. So as you can see, the libraries are the same ones that I mentioned before, NumPy, Pandas. You can still use sklearn. And here we have TensorFlow as TF. So this is an important library that we're using. And then we have our metrics libraries, the confusion matrix, F1 score. And we also have the functions for label encoding, standard scalar, and train test split, all right, for splitting our data. The learning rate, I've already explained what this is. Always remember the step of the giant over the mountains, right? So it has to do with the optimization algorithm, gradient descent. Number of epochs is the number of times that we're going to repeat this training, so it's going to be 5,000. The convert one hot function here does the one hot encoding for the labels. Remember how that works. Keep in mind this is just simple code so that we can understand how the algorithm works, but I do strongly recommend that when you write your code, your algorithms, that you use the built-in TensorFlow function one hot. Right, so I do suggest you use this one instead. Then we have, the basic steps. This is the approach we have taken with sklearn and everything else. We read the data, so the data is in log file features.csv. You can see that here. So we're going to read it using gen from text into feature. Notice here we indicate that the delimiter is a comma, and we indicate that the columns, used columns, will be all the columns from from 1 to 1001. So the features in our data set. This, remember, assumes that column 0 contains the labels. And we're going to read these as integer because they are basically counts, if you remember from our count vectorizer function. We also read the target with gen from text from this file. The delimiter is comma separated. And notice here we only read column 0. Data type is integer. All right, then after that, we've read the data, so we can start to pre-process the data now. So let me add a line here. So this would be in our pipeline, the pre-processing data or cleaning of the data. So standard scaler, if you remember, this is for when you want to normalize your data, right? So remember, you have two features, one in a range from 0 to 65,000, one in a range from 0 to 10. So there's big difference there in the ranges. So this process basically maps those feature ranges to ranges that are consistent, that they have the same dimensions, basically, 0 to 1 or something like that. So for that, we create the standard scaler, then we fit the data with feature, and then we transform, once we've trained it, basically, the SC object, the standard scaler, apply it to feature, and we get our new feature normalize. Okay, so that normalizes our features. Then remember, for this step is new, whenever we're using deep neural networks and TensorFlow, we need the labels to be one-hot encoded. So we're going to take, first we're going to take our data and apply fit transform. We're going to use the label encoder just to make sure that, if we had good, good, bad, bad, it becomes 0 and 1, 0 and 1. Right? So we encode the target into target label here, and then target label is passed through the convert one-hot function, and that creates a new variable, target one-hot, which is the one-hot encoded vectors, basically. So this, if we don't do this step, it's the TensorFlow will not be able to process the labels. So the labels do need to be one-hot encoded. All right, once we've done that, we are ready to create our train and test sets. All right, so you can see here, remember that in sklearn and TensorFlow, we need to have an X matrix and a Y vector, all right, for each data set. So in this case, since we're creating two sets, a train and a test set, we're going to end up with 4 variables. You can see that we have that here, X train and Y train one hot, and then we have X test and Y test one hot. Okay, so all we have to do is we call the function train test split, takes in as parameters feature normalized and target one hot, and then we specify that we want to split. We want a 25% split, all right, for the test set. All right, random state equals 0. All right, so we perform this, and now we obtain our 4 variables, and we are ready to do our deep neural network. All right, here in this step, I'm just going to print or obtain the values of the features on the column. So here, remember, we grab X train, and we look at the Y axis, basically, the shape 1, and we can, by doing this, we can count how many columns are in X train. All right, so X train is the feature, so that basically means that we know the number of features by doing this. And then the same applies for B. We take Y train one hot, all right, and the first row basically of Y train one hot. And so by doing the length, we can also know the number of classes in that vector or that matrix, Y train one hot. All right, so this will give us the labels. All right, so now that we have it, we can do print A and B just to double check. I do strongly recommend that you do this just to check that, if you know your data set. For instance, our malware data set has 1,000 features and 2 columns, or 2 classes, sorry. So you should get here, when you print this out, a 4 and a 2, okay, as your output. We run it, this print begin, and so now we are ready to run our code. All right, notice down here we have the familiar function print stats metrics. So hopefully this is familiar to you now. This function is for printing out, the precision, recall, F-measure, confusion matrix. All right, we also have the other function we saw before for plotting our data. So plot metric per epoch. So this is very useful for printing out the chart of the deep neural networks, so how it learns over time, and so this is very, very handy. So keep in mind, we keep track of something like accuracy scores list, some kind of an array that has to be global to this function. We iterate through it and extract the index, which is equivalent to the epoch, and the value, and then we can plot those by using the PLT or plot object and matplotlib. All right, so that's pretty much all the helper functions. Now we are ready for the deep learning part. All right, so this is deep learning, all right, and this is actually, where we start to define the architecture. So if you remember in the video, we had a helper function layer. So we use this function layer to be able to map any layer to the next layer, right, in a neural network. So it can be input to a hidden layer, or it can be a hidden layer to another hidden layer, or it can be the last hidden layer to the output. So this function is very useful for that. All right, and so this is our layer function here. Okay, so we have the layer given some input, right? That's the previous layer. And then we define the next layer. So using the weight shape matrix and the bias shape, right, we can predict, right, by using this. So we do return TF NN ReLU. Okay, that's the activation function that takes in as input TF matmul, which performs a matrix multiplication of whatever the input is with the weight matrix plus the bias, and that is going to be equal basically to our y hat. So if you remember, this was the y hat that goes through the activation function, and so that is, now the new output, the new y output. So if you remember, this exact same function was discussed in one of those videos. Here we define the parameters, so we need to define W and B. So let's start from the bottom, and let's look at the bias, for instance. Remember, we use get variable. We define what this is. It's just a way of reusing functions. So this is a node in the computational graph, remember, called B. It's going to be of bias shape, so whatever this is, all right, which is usually the number of neurons of the 2 layers, not the input layer, but the next layer. All right, so we need to define, we just leave this as a parameter, bias. We use an initializer, bias init, which basically is a way that we can set what we want to initialize this tensor. And so here we say that bias init is nothing more than just a constant of value 0. So constant initializer, value 0. Right, the same applies for the W matrix. It's pretty similar. Get variable, the node is called W. The weight shape, remember that this is we have 2 parameters here, an I and a J, if you will, to define the shape of the W vector. Okay, remember that this is also discussed in the previous video, but let me just do it here, kind of in a comment. So weight shape looks something like this, if you remember. So something like, let's say, 5, 2, or 3. And that just implies that you have 2 layers, this layer and that layer. The first layer has 5 neurons. the next layer has 3 neurons. All right, so that's really what you end up with. And so the weight matrix needs to be able to connect all the neurons from the previous layer to all the neurons of the next layer. All right, so that's what is happening there. We need to provide that parameter. And notice that the initializer is winit, basically. So here winit is a little bit more complicated. Instead of initializing this matrix weight, or W, sorry, to zeros or whatever values, we initialize it using a random normal distribution. So we need to specify some kind of standard deviation. So we just put in some value here based on the weight shape parameter. So based on the shape of this, right? Based on the shape of the weight shape dimensions, we can specify a standard deviation, and then that standard deviation is used for the random normal initializer. All right, so these are parameters here that you kind of have to play with. There is no science to these necessarily. It's more of a little bit of an art. But usually when you do better initializations, your algorithms may perform a little bit better. All right? But anyway, so that, this function, as I said, it's already discussed in the video, so I don't really want to spend too much time in it. And instead, I just want to go over the solution of this lab. All right, so once the layer is defined, here I do have an example of the actual architecture for this deep neural network. Let me move it up a little. Okay, so I can fit everything in it. So notice it's just a function, the inference function. I gave it a new name like deep layers. This is X, right? XTF, so this is your training data. All right, and then we just specify the number of features and the number of columns, which will be our A and B parameters. So remember in that lecture I discussed how this works. So basically I will just say that this would be a good moment for you to maybe stop the video and look at this piece of code and try to draw it out on a piece of paper. So try to draw out the architecture, all right, of this, because as I said before, for the most part, whenever you're building deep neural networks with TensorFlow, you're going to be reusing the code quite a bit. And the only things that are going to change a lot are things like reading the data and putting it in the specific format, reading the data in batches if it's a lot of data, and this part here, right? So selecting the architecture that you want to use. So I would recommend at this point, as I said, stop the video, think of what XTF is, and features, and columns, look at this architecture here, and try to draw it out and see what the architecture for your neural network is. So you've had a few minutes to think about the problem in the lab, right? So you looked at the architecture and the code, and I asked you to draw it on your piece of paper. And so I'm going to do the same. So hopefully you're looking at the code as I am. This is for the architecture for malware, right, and deep learning. So the architecture should be, we have the first input layer. We have input, all right, and this has neurons. So XTF is coming here, right? So XTF is our data. It's going to be loaded into every row. Every row in that data set is a vector that goes in here. And so the dimension for that is A. And we established that A is 1,000. All right, then the next hidden layer, hidden 1, it's a much smaller one. Why did we choose a much smaller one? It's just an example. Sometimes when the problem is very easy, you really don't need that much. As I said, this is more of, I'll even write it out here. This is more of an art than a science, right? So you have to do a little bit of trial and error to figure this out. But anyway, this is size 30. This is hidden 1. Then we look at the next one, hidden 2. takes in the values from the previous layer, which is 30, and now it is size 25. Then the next one, hidden 3, is going to be, so the previous one is 25 nodes, and it is now 10 nodes. So this is size 10. All right, this is a neural network with 4 hidden layers. So that's going to be, the previous one has 10, and now this one has 5. So this is only 5 neurons. And then the last one, the last layer, is output. And this layer, the previous layer that it's connected to, has 5. And now this one is B, right? And this B is, we established before from the code that it should be 2. So I do suggest that you print out these 2 values as you're doing your analysis, all right? But they should be 1002, all right? And if I got everything correctly, that is the architecture for this neural network that you've built. So what I would recommend is consider other neural networks, right? Consider neural networks, maybe even just a one layer, right? A neural network. And then, play around with other deep neural nets, maybe 2, and so on. All right, so this is what you should do for your lab. So try other architecture. And this is where you're actually now building, for the first time, deep neural networks. All right, so hopefully now you've had a chance to look at it. And now I'm going to proceed to draw it. So I'll explain what it is, but basically, I'll have the first layer, the input layer that is going to be of size n features, right? So that's why this is here. So n features means that that's the first layer, the XTF, and so I need to draw a layer with that number of neurons. However, my next layer is only of size 30, and that's really a choice. It could have been bigger, it could have been smaller, and that's why I want you to play around with this. All right, so it doesn't, our input is 1,000 features, so our next hidden layer doesn't necessarily have to be so small at 30 features. You can try a bigger number, like 400. So you can make this 400, this 300, 200, and so on. So play around with these architectures. But remember that in general, what you do want is you want to have, if your input layer is 1,000 neurons, then you want the other neurons to get shorter or smaller as they progress. So reduce them in size by half, maybe. So go from 1,000 to 500, from 500 to 250, and so on. And if you remember in the video, I said that the goal of this is to force the machine learning algorithm to learn with less. All right, so anyway, so we have here hidden 1, XTF, number of features, which is 1,000, and then the dimension of the hidden layer 1 is 30. Remember, this is the bias, and the bias always matches the output layer. So these two match. Then the next layer, of course, when we define hidden layer 2, it's going to look at the previous layer. The previous layer is 30, right? So then this has to be 30, and then the next layer, the new layer, hidden 2, is 25. And we keep going that way. The next layer is 25, right? This layer is 25. And 25 ties to a new layer, hidden 3, of size 10. And then we continue like that. Hidden 4 connects to hidden 3 of 10. We define that hidden 4 is of size 5. And then finally, hidden 4, which has 5 neurons, is connected to the final layer, which is of size n columns, which is 2. So that's basically the architecture. As part of your lab, I would suggest that you try several layers, fewer, more, and with different neuron configurations, and see how that affects your results. Okay? Now everything else that I didn't explain in this function has already been explained in the lecture videos. All right, then I move on to the loss deep. All right, so this is the loss function. Remember here we take the output, which is the y hat, the predicted value, and the real labels, right? And instead of building the math functions here, we just use the built-in TensorFlow loss function. So in this case, we're going to use softmax cross entropy with logits. It takes in this input, output, and YTF, right? And that's going to be what we try to minimize here. So we have our function defined. And then we have the training. Remember, in the training, all we do is define that we're going to use gradient descent optimizer or atom optimizer. That's another one that we can use. We use the learning rate, and then we basically minimize cost. Remember, this cost is this one, right? So loss. So whatever loss returns is fed into cost here, and we'll see that below. And then we just return this object. So that this node, so remember, all of these are nodes that we're defining in the computational graph. So it's like we grab the whole node and just move it somewhere else. All right, and then finally, evaluate. This is our function, already explained as well. It just takes in the y-hat, the predicted labels, the real labels. It applies argmax because remember that output and YTF are one-hot encoded. So it just has to get the maximum index, or the index of the maximum value in each row. Right, so you have 0, 1, 0, then it's going to take that 1, which is in the index position 0, 1, 2, so it returns 1. All right, so now that basically converts one hot encoded, which might have 3 columns, into a vector that only has 1 column with the labels. Then you compare with tf.equal. Right, remember this is one of the functions in Appendix B of the book, and examples are there of how that works. All right, so this then, once you've compared them, correct prediction basically gives you like a Boolean list of how many matches you had and how many values you had that were not a match. And that basically is similar to calculating accuracy. So then we can just take correct prediction, cast it to float by doing this, and then by applying reduced mean, we can get a percentage, which basically tells us, out of all, how many were true, or out of all, how many were matches, and that's our accuracy. Keep in mind, and I'm going to jump a little bit ahead, that we also have this piece of code here, YP metrics. So YP metrics is just a simple function that takes the one-hot encoded output, the y-hat, and converts it to vector. So the same thing that we did here, so this exact same thing we did here, tf argmax output 1 is what we're doing that down here, tf argmax output 1. So this function is just so that we can again take the predicted labels that are one-hot encoded, and make them into a just one column vector called YP metrics, because this is what we're going to use with our functions. This one, print stats metrics function. Remember this we already discussed as well. We take the YPred and the Y-test. So now that we've talked about evaluate, we are ready now to define our placeholders. Remember, placeholders store the data. So here we define XTF and YTF. They're both float and they are of size none. Remember, placeholders are none, because you can have as many rows as possible, and then the size of the columns for X is the number of features, A, and the size of the columns for YTF is B, which is the columns, because this is one-hot encoded. The next step is where you have the core functions here, right? And this is where we call everything. So notice here, first we called inference deep layers, right? We give it as input XTF, that plugs into the computational graph. We provide A and B, which are the features and the classes, and that is tied to the y-hat. So remember, this is very equivalent to something like y equal mx plus b, right? That's very similar to that, except that because it's a deep neural network, it starts to become something like this. So now we have hidden 1, which is going to be equal to another set of m, but now instead of x, it's going to be this one. So this is really hidden 1 here, and this is hidden 2, and then this becomes hidden 1 plus b. You see, so it's a deep neural network in that sense, that the outputs of one layer are connected to the inputs of the next one. that is inference deep here, so it defines kind of the y equation. Then we have the loss function. Remember, that just takes output, which is y hat, compares it to the real labels, ytf, and it tries to minimize the loss function. And then we have our training, which is where we call gradient descent. We give it cost over here, right? That's the thing that we want to minimize. And cost returns the node train op. So train op is the node that we are going to run, right? So train op is the node that we are going to run. Okay, and then finally evaluate just takes whatever's in output, compares it to ytf, and that returns eval op. So these are as discussed in the lecture video, these are the nodes in the computational graph that we can run to see our results. Finally, remember that so far all we've done is define the computational graph. Now we are ready to initialize everything. So we create the session, tf.session, and we run it, and we give it as parameter init, which stands for tf global variable initializer. Right? So global variable initializer just takes all the placeholders and variables and assigns data types to them and so on. I already explained this part. This is the YP metrics for the evaluation. So remember, this is like taking y hat, and it basically converts from one hot to non-one hot. And finally, we are, that's it. So the code is actually pretty straightforward. As you can see, building a deep neural network is not really that difficult, right? And for the most part, you will just be reusing this code. The challenges, as I said, will be later on when we start to read in larger amounts of data. Obviously, if you were doing more advanced deep learning, like convolutional neural networks, etc., then it does become a little bit more difficult. Not difficult, but just there's more to it. All right, so now that we're ready, that the computational graph is ready, that we have a session, we are ready to run our code. So we just go over here to the main loop. Okay, so our main for loop. Okay, you can see it here. So we do this for loop in the range of n epochs, which is 5,000. So we do for I to 5,000. All right, we print basically here the current epoch out of n epochs, and then notice here we just run the session. So we're going to do a session.run. Okay, and what do we run? We run train op. What is train op? Train op is this one here. Remember, and basically when you call train op, you're calling training, which is basically calling the gradient descent on this cost, which is what you're trying to minimize. And remember that the cost is just like with linear regression, where you have a y hat minus y square, and you minimize that for linear regression. Here, we have a built-in TensorFlow function. All right, so we take the loss function. So the loss function is referenced by cost, and it's minimizing the difference between output or y hat and ytf. And output is connected to the inference function. So this output here is connected to this inference function, okay, which is, as I said, the y equal mx plus b, and so on. So everything is connected in the computational graph, and that's what we are calling. So we can call everything basically in that computational graph just by calling train op. So we're going to do session run train op. Remember, we also have the feed dictionary. The feed dictionary takes the data set here, x train and y train one hot. Remember, these are the data sets from the train test split, right? So when we did the train test split, we got these 4 data sets. Those are the ones that we're using now. So in this step, we do session run train up in the feed dictionary. We provide x train to the placeholder xtf and y train one hot to the placeholder ytf. All right. Then we print some some lines here, so just to make this more readable. And then we run notice that I don't need 2 for loops here. I can train, and in the next second I can evaluate. So now I run session run. Notice that now I'm running actually 2 nodes, eval op and also YP metrics, right? So I run both. And the results of eval op go into result, and the results of YP metrics go to Y result metrics. Okay? The feed dictionary now has changed. Instead of X train and Y train 1 hot, it is now X test and Y test 1 hot. And that's basically it. So once we run eval op and YP metrics, we have our results. The value that we get in result, we just print out here. And then the value we get in Y result metrics, remember again, Y result metrics is basically just taking the predicted output, which is 1 hot encoded, and converts it to a non-1 hot encoded version. So it goes from 0, 1, 0 to just 1, or 1, 0, 0 to just 0, or 0, 0, 1 to just 2. Right? So that's all that's happening there. So once we have YP result metrics, we have that. Out of convenience, I renamed YP metrics YPRED. Okay, so we just rename it. So it's consistent with what we did with sklearn. Notice here that, so this is the predicted. This is the predicted here. And then this one up here is the actual, right? So this is the actual data, Y test 1 hot. And so we can, again, this just converts it from the 1 hot encoded version to non-1 hot version. So now we have Y true and Y pred, and we can compare them. So this is for the test set. So we run print stats metrics. We give it the Y true and the Y pred, and that will run our familiar function for getting precision recall, F measure, and confusion matrix. And then the last part is that we are going to plot. So at the end of the code, you could change this to say every 1,000 iterations plot, just to see how things are doing. Or we just, here for our example, we plotted basically at the last iteration so that we can see a little graph. All right, so that's basically the code, the deep learning code for malware, for our malware analysis problem. So let's go ahead now and run this, and let's see what we get. So I'm going to do Control X, enter. Okay, now I'm going to go ahead and run this code. All right, file is TF. All right, and there we go. It's running. So it's going to do this. Notice the precision and the recall, right? So here you can see it's actually in the 0. See how it's 0 still. We're currently at 200 iterations. It's still F measure, recall, precision or 0. The confusion matrix doesn't seem very good yet. But keep your eye on those values in the precision, recall, and F measure, and they should start to pick up eventually. All right, so as you can see, I stopped this at 1,604 iterations. This happens sometimes, actually. I'm glad it happened, because sometimes, and this is where the initialization of the parameters, those init parameters that we had in the layer function, are actually really important, because the way that we initialized the data this time, the algorithm basically wasn't converging fast enough. It wasn't really learning. So I'm going to try this again. All right, and let's see how it does. All right, so it's still at 0 at 130. It should eventually start to pick up. So at 300 iterations or so, it should start to pick up. All right, and you can see here this iteration is a little bit different, and now the values, we are at 100 or 200 iterations, and now we have a precision or recall and an F measure. So deep neural networks are sometimes a little bit finicky like this. It wasn't learning before for the way we were initializing it. Now it is learning, and so this can happen, and that's why as a data scientist you have to basically work the problem, right? You have to work the problem, run a few trials, and that's one of the advantages of TensorFlow, that it gives you all these tools to address these kinds of issues. So in this one, we can see now that precision, recall, they're starting to pick up a little. Okay. Now keep in mind, this data set is a little less academic, our malware example, so our values are not going to be all above 90, or may not be all above 90. So as we start looking at more realistic data sets, especially when you start looking at your own data, you may find it a little bit more challenging to get values that converge and give you really good results. And we are done. So as you can see, a very interesting graph actually. I kind of like this graph. It shows you, the behavior. So the gradient descent algorithm struggled a little bit, right? It seems like it jumped really high at the beginning, then it wasn't learning at all, and then it started to learn again. So it started to converge again, and you can see the behavior of the graph there. So you have it dips, and it never went past like 81%. So, okay. So that's the result of the graph. Here are the final results at run 5000. Accuracy was 81. The confusion matrix had 7 misclassifications here. Precision was 65. F measure was 78. Recall was 1. So can you improve these results? Well, give this a try. Try other architectures, other more or less or fewer hidden layers, more or fewer neurons. Play around with your architecture and see what you get. So let me go back to the code one last time just to kind of point out a few things. So here, things that you can tweak a little bit. You can change the learning rate, right? So maybe add another 0 here, see what happens, or make this, so try other values, right? So try 0.1 and see what you get. Try 0.01 and so on, right? So try more and see what you get here. Try more epochs or fewer epochs, right? See what that gives you. All right. I do suggest you use the built-in TensorFlow one-hot encoded function. Try that as well instead of this. There are other ways of reading in data, so you can always experiment with that as well. Here you can leave the scalar. That I would recommend that you should always normalize your data. We did the label encoding. I would suggest that you try to print these values. Now, it's nice that we can, these are not TensorFlow nodes, these are just sklearn variables. So these are easy to print out. Unfortunately, one thing that you should always remember is that it's sometimes difficult to see what's in a tensor. All right. So a few tricks with that is you can always print out the dimensions, but it's not so straightforward usually to visualize what's in the tensor. But at least certainly here you can print out these variables for the labels and the normalized data just to get a feel for what's in there. Other things you can change, you can plot, instead of plotting, here we were just plotting the accuracy scores. You can try to plot also the precision, the recall, the F measure. So just, same approach, just create a new list and see what that gives you. And here, of course, you can modify these, what I was saying. Try more layers, fewer layers. Remember, you just have to remove the ones in the middle. You really just need to have the input layer and the output layer, right? So you need to have this one output and the first one, and then in between you can decide how many layers you're going to need to use or want to use. So here you wouldn't really change anything. I did suggest you change the learning rate at the top of the code. Here, these are the sessions, so there's nothing much that you can change here or here. But anyway, so those are some recommendations that I make to you to see if you can improve your results. So in conclusion, these were the results of our code, or of our TensorFlow example from Malware. As you saw, we printed out precision, recall, F measure, the confusion matrix. We also printed out a graph. And so now as a data scientist, what you have to do is you have to interpret these results, right? So you have to interpret them. And so I would say it seems like with the F measure of 78% for a 2-class problem, okay, it seems like this could be okay. As a cybersecurity professional, you probably have to add a little bit more judgment there and say, how helpful this will be really for your task. All right, so hopefully that made sense for you. This was our doing malware analysis with a deep neural network in TensorFlow.